All right. So for all of y'all who haven't really looked at SKUTs before, I'm going to pull this back up. So I type in the ARL SKUT laboratory. This takes us to NOAA here. And we can go in and we can add in an airport here for ease, or you can do latitude, longitude. For us, I'm just going to do SBA for Santa Barbara. We go down to the soundings here. There are a bunch of different models on the left-hand side. Spatial resolutions of the models next. Temporal, like the time span over which they predict, and the temporal resolution. I'm just going to go to the first NAM here. 12 kilometers, 84 hours, 3 hours. Go in. This is the start of the forecast. Click next. I want JavaScript.
Eggman, before you keep going, I know there's a bunch of people that are asking for recording. You cool with that?
It is recording right now.
Oh, it is? Okay.
Yeah, I did hit the button. Should be recording, yeah.
Yep. I'm an idiot. I'll shut up.
Cool. It's all good. It's all good. So then you type in the code here to make sure that you are not a robot. No, it doesn't like me. Is it because of this? That's very weird. Well, whatever. When you click on all those buttons, it gives you one of these. It'll have. That's really annoying that it doesn't work. I'm gonna try this one more time. 0 GATT. Cool, here we go. All right, so this is the SKUT currently for here in Santa Barbara, okay? And so we come in and there's a couple of things we're gonna be talking about. And the red line is the temperature profile of the atmosphere. The green line is basically a measure of how much water there is in the atmosphere as a function of temperature. And really, we could sum this talk up really simply by basically saying that if you want to know if the lapse rate is going to be good for the day, you basically want it to follow these lines that are here. Okay, these are called the dry adiabatic lapse rate lines. And basically, we just want this red line to be parallel to them. So we want it to lay over so it looks much more like this. We all like looking at good lapse rates. Like this is a fantastic lapse rate, right? Like this red line is leaned over and sort of matching this dry adiabatic lapse rate line, okay? So if we wanted to know sort of like how far the air would rise in a day, we would literally we would come over here and we would figure out what the ground temperature is going to be. And let's just for ease, let's say it's 40 degrees. We would take this down to the ground. And the way this graph works is then we would follow it up the dry adiabatic lapse line until it meets this environmental lapse rate. And basically that's how high the thermals are going to rise, okay? So simply, like if we go look at this on any day, the more it's leaned over this way, the better it is. The more it's leaned over this way, the worse it is, okay? So it can be relatively simple to try and look at lapse rates, but I want to try and describe today why basically we have this line right here that we follow and why it's pretty relatively constant, okay? Like truly, why are we just doing this simple conversion of a temperature on the ground? Basically what it's doing, it's cooling as it goes up until it matches the same temperature as the surrounding air of the atmosphere. So let's switch screens here.
Hey, Chris, dumb question inbound, just real quick to ground me here. Is this, are the red and green lines just theoretical or projected models, or is that data that's coming from like weather balloons?
So this this is from the NAMA model. It's the North American model. So it is a modeled lapse rate of the atmosphere, and they work. I mean, they work pretty good. It's sort of like another discussion we can end up having. But yeah, this isn't an actual piece of data. The only actual balloon we have is from Vandenberg, but it's pretty far away. It doesn't really represent this area super well. I think represents pretty well for trends. Then again, I think some other people might be able to answer that question a little bit better too. We can talk about that more at the end. Really, I don't really look at forecasts all that much anymore. Okay, so you can all see the iPad screen now. Yeah, can we?
Somebody's keying the mic.
Yeah, we can see it.
So we can see this now? Okay, cool. All right, so basically the landscape that we're going to talk about here is so I'm going to talk about basically a parcel of air. We've talked about this before, but the parcel of air is simply just a piece of air that would be heated on the ground that would rise. It basically indicates our thermal. So, yeah, let's see who that is. Someone's making a lot of noise.
Chris, I think you can mute everybody. You can mute everybody.
I think that's Miles. Yeah, thank you.
Whoever's in their car is keying the mic.
Okay, I'm not in a car. Somebody told me it was me, but I don't think it's me.
All right. Well, it's quiet now. Okay.
George?
So the idea is of how this system basically works, okay, is we have a sun out in outer space that is shooting a bunch of energy at our ground here, okay? And because the air is not dense enough, it actually doesn't really receive the radiation of the sun. But the ground is definitely dense enough, okay? So the ground ends up heating up, okay? And through that, it'll end up heating the layer of air right at the bottom, okay? And so this is where we have this idea of our little parcel of air, right? We're just thinking of one of these little pockets of air on the ground. And this is basically, this interaction right here this is going to be conduction, right? The air is actually touching the ground. So the air is being heated the same way as a pot on the stove. And then once that air is warmer than the surrounding air, it'll end up rising, okay? And as it rises into the air, it expands and it cools, okay? And so first of all, we want to talk about why does the air parcel actually end up cooling, okay? And so the reason for this is, and the reason that it's called an adiabatic lapse rate is because, so this is one of the processes in thermodynamics. It's basically described by the first law of thermodynamics. And it's this idea that, so as we go up in the atmosphere, we end up expanding, okay? And when you expand, when you change your density, in order to do that, it takes a certain amount of work, okay? And so we can talk about this change in density equaling work, okay? And anytime you have work that occurs, the way that it happens is it happens because of a change in temperature. And sorry, this delta here means a change in, okay? And so basically, anytime we have this parcel going from smaller to bigger, the work that gets done to expand this, okay, decreases the temperature. And a good question to ask is maybe, why does it not cool sort of the air around it? Why does it only cool this parcel? Why do we call it a parcel? Why is it isolated? And the reason for that is that truly, as this parcel of air becomes less dense than the surrounding atmosphere, it is actually very well separated from the surrounding atmosphere. The parcel of air basically doesn't exchange temperature so well, or like it exchanges temperature with the surrounding atmosphere so poorly that we don't even need to actually consider it in our equations, okay? And so that is truly the definition of an adiabatic process. It is something that if you do work or change the temperature within the system, it does not interact with the outside system, all right? And so we can also have the opposite occur, that if we go from something larger to something smaller, the work that is done on this will end up increasing our temperature, okay? How do people feel about this so far? Do you have any questions about that? Feeling pretty good? All right.
I was just wondering why the parcel expands as it rises. Is that just because the temperature differential between it and the surrounding air?
Yeah, we'll talk about that right now, actually. It's a great question. Yeah. So the idea is that as the air starts rising, it expands because it wants to equalize with the surrounding air, okay? And so basically we have this, pull this up right here. So on the left-hand side is the altitude. On the bottom, we have density, pressure, and temperature. And basically the three lines that end up, this is actually, the three lines that are right there, okay? We can see that they're relatively constant in the lower atmosphere, okay? And the thing that we want to pay attention to is basically like density and pressure all, and temperature, density, pressure, and temperature all change at a relatively constant rate in the bottom of the atmosphere. And so, my computer's doing things. Sorry, 1 second. And so, as that parcel of air continues, all right, so actually let's talk about why this is real quick, okay? So why does density change as we move up in the atmosphere, okay? And so the idea for this is that air is compressible, okay? First of all, density, density is a mass divided by a volume, okay? So if we, basically what we're gonna talk about is the mass of the atmosphere is gonna be relatively constant, but if we decrease the volume of the atmosphere, we decrease the number in the numerator, it'll end up making the density higher, okay? And so the reason that the density increases in the atmosphere is because the atmosphere is compressible, all right? Not all things are compressible, like solids are not compressible. I think a useful analogy to use here is sort of like if you have water in a cup, water is not compressible, right? You can't push down on it if you could make a perfect seal. But if you had water in that same cup, you could actually push down on that water and compress it. And because it's the same amount of mass in a smaller volume, you just increase the density of that. Okay, so in our atmosphere, what would be decreasing the density of the air? And it's simply that if we have a giant column of air here, right, from the bottom of the atmosphere to the top, we have gravity pulling down on all of this mass here, right? So these are two forces. We have gravity and all of the weight from here to, let's say, here, pushing down on this here, okay? And so it's the same thing as my air in a glass analogy, right? If you have all of this right here, all of this mass pushing down on the bottom, you will end up compressing this piece at the bottom, okay? And we feel this weight all the time. The weight in general, or on average, is 1,000 millibars or 14.7 psi, okay? And that is simply the weight of the atmosphere above us that is pushing down on us right now. It changes very, very little for the most part between like high pressures and low pressures. It's not something that we really notice. But someplace that you would notice this is that if you went swimming, right? And the further you go down in a pool or in the ocean, you don't need to go very far to feel the crushing weight of the ocean. And that's simply because the ocean just weighs more, right? And so it's this same concept that we're trying to talk about here. So if we're talking about at the bottom of the atmosphere, we're going to have a lot more compression than if, let's say, we were talking about a piece that was in the middle of the atmosphere, right? Here we have a lot less mass pushing down, that gravity pulling it down. So this piece here will be compressed a lot less than this piece over here. And so that's why as we go up in the atmosphere, if we make this altitude, which is Z, and this density, right? As we go up in altitude, we end up increasing our density at a constant rate because as we go up here, we're just decreasing the amount of mass above us at a constant rate, okay? So basically, the picture that we're trying to paint here is that, I'll put this back up here, Z. So as our parcel of air rises up through the atmosphere, so it starts here, right? And it starts going up in altitude. It's gonna want to equalize with the surrounding atmosphere. And therefore to do that, it has to become less dense. And as it becomes less dense, it ends up doing work. And because work occurs in this case and we're expanding, it equals a decrease in the temperature, okay? And so that's why in general, as air rises, it cools. Now, if we take that stuff with this column here, right? All of this stuff right here is called that is the hydrostatic equation. And it relates the pressure down here. It relates the pressure to it's basically a function of density, gravity, and height, right? Because the height is directly proportional to the mass above you. Okay. If we take who's talking now? That person. So if we take that with this up here, which is the first law, thermodynamics, which basically says that a change in the internal energy must come from either heat or work, okay? If we take these two together and we do this lovely thing called math, all right? Basically, all these equations ends up simplifying down to one term that describes our lapse rate, and that is G over CP. And so G is and so basically the idea of this is that like this right here and this right here, they're represented by equations, right? And so if we take an equation that is, or if we take something that's like 5 plus 1 over 5, right? The 5s cancel out and we end up just being left over with the 1. If you do that with these two equations, you end up getting that the lapse rate, which we described is basically derived by these two equations, ends up being G over CP. So G is the force of gravity, and CP is the specific heat of air. And all that is the amount of energy that it takes to decrease or increase something by 1 unit of temperature. Okay. And so what is this saying to us? Basically, it's saying the amount of energy that it takes to lift something against gravity. Okay. Which I think it's very cool that all of those things follow the equation and it's very simple. But the rate at which this is, so G over CP ends up being 9.8 degrees C per kilometer, or if you want to be really annoying about it, 5.5 degrees F per 1,000 feet. Okay. So once again, I'm just gonna start a new page. So again, we have our sun up here, which shoots a bunch of photons down at the surface. We end up heating our surface, which heats the air directly above it. As that air becomes less dense, it rises, it does work, and it cools at a rate determined by gravity divided by the specific heat, which equals 9.8 degrees C. So this is the dry adiabatic lapse rate. And that's really important because a wet adiabatic lapse rate is actually something completely different. Okay. Questions from here? How are we feeling about this?
So Chris, when we talk about the dry adiabatic, that's kind of the standard model, right? That we use to gauge the lapse rate. But is that something that we would encounter in real life? Is there such a thing as a dry adiabat, or is it likely that we're going to get something that's got some moisture in it? And how is that different? Or are you going there?
I will go there, and the term dry and moist is a little misleading. The point at which we switch from dry to wet is only when condensation occurs. It doesn't actually represent the moisture content of the air. It does a little bit, but like, let's keep this simple. Basically, the only reason that we switch from a dry to a wet is because we have condensation occurring. And yeah, I mean, we do use this. Like this is on our SQT, which we'll go back to later. This is that line that we are comparing the environmental lapse rate to. This is what we are comparing the temperature of the atmosphere to, and this is basically the maximum lapse rate that you can get, and this is really what we want to see. Anyone else?
So that represents that line that we're going to follow after we hit the ground on this QT, we follow up.
Exactly, Lucas. That is exactly the line that we follow up, yeah.
This is the maximum possible lapse rate? No.
Yes.
Yes.
Yeah.
You can't go drier, or if you have more moisture, it actually reduce lapse rate, right?
It does reduce it, yes.
And that's constant through the atmosphere?
It is, because it's a function of density, right? And so as I showed in that one graph, the change in density with the atmosphere is constant because it's simply really just a function of height, mass, and gravity, which as we go up are all constant things, or constantly changing. Okay, so.
Hector, why do we talk so much about 3 degrees Fahrenheit per 1,000 feet?
You know, I'm not exactly sure why we say those things that we do. Someone else might have a better answer to that than I do. Ravis or Logan, do you guys have a better answer for that?
It was what is the temperature of the lapse rate? I kind of missed the beginning of that.
Like why do we go with
why do we talk 3 degrees Fahrenheit per 1,000?
So 3.3 degrees Fahrenheit per 1,000 feet is what we consider soarable, just because that's the velocity in which we can actually maintain with a with a paraglider that's descending at 1.5 meters a second. So that's a different number for different aircraft.
Cool.
Does that make sense?
That's awesome.
So if I did my math right, 9.8 Celsius per kilometer is 5.5 Fahrenheit per 1,000 feet. So
Yeah.
I'm surprised that 3.3 works. Like I would think we would need more than 5.5 in order to lift something. Am I thinking about this the wrong way?
So 5.5 is the maximum. If it's 5.5, you're going to be skyrocketing. So a number like we would likely be soarable with a number less than that, right? We don't need the maximum lapse rate in order to be soarable at all.
Okay, thanks.
I think also there, it really depends on what you're looking for in conditions. 5.5 being kind of that more standard number is a really good day. We normally, desert days, we really like 6 degrees per 1,000 feet. But anything over 4, I'm willing to drive, couple 2-4 hours to get to.
Yeah. So let's see. I'll go back over to.
And can you actually tell what the lapse rate is right on this QT if it's like at 3.3 or over 4?
Yes. Yeah. So let's come back to our lapse rate over here. Okay. So again, these dry adiabatic lines, which we would expect to be constant, are these gray lines right here. Okay. And so the way that you have to view this graph is that anytime you want to understand what the temperature is, you basically have to follow this to a temperature line and then go up. Is that right, Logan? Then from here, if you want to understand the temperature, do you follow this down and then up? No one's paying attention. Anyways.
No, I think that's right, Chris, is basically where those lines intersect. That's the temperature that you would encounter at that altitude along that adiabat.
Yeah, I guess I forget how to go in the opposite way, but that sounds good. But so again, if we want to understand how far an air parcel is going to rise, just to make it easy, we can say that it's 40 degrees C. Okay, we come down until it hits the ground, and then it's nice that these two intersect. And then we just say that it's going to cool at this constant rate, which we just determined, which is the dry adiabatic lapse rate, until it ends up hitting this temperature line, which this temperature line represents basically the temperature decrease with altitude that actually occurs in the atmosphere. Okay, and we'll talk about that in a little bit. And so once these two end up reaching the same temperature, the same density, the air will stop rising. Okay. Here we see that there is normally we consider this like a bit of an inversion, but actually necessarily what's going on down here doesn't necessarily matter as long as you have a starting energy that will allow you to go through that. Okay. Obviously 40 degrees Celsius is super hot. So it's not going to happen. On this day, air really isn't going to rise very much. It's probably going to be something like this to here. But nonetheless, okay, these lines exist on here. And basically we want to know our starting temperature of the parcel, what the temperature is on the ground, the amount of energy that has lifting off the ground. It'll cool at a constant rate, until it ends up hitting this. So again, hopefully that'll help you understand better why if our environmental lapse rate is leaned over sort of so it's looking like the dry adiabatic lapse lines, that's why it would be a really good day. If it's straight up and down, I like to say it's good and no in Santa Barbara because it really sort of could be leaning a little bit left or a little bit right. But if it's actually leaning right, like it is here, right, we know that the amount that air can rise is going to be significantly diminished. And that would be a stable day. Okay, so let's talk about.
Hey, Chris, just quickly. So again, the soarable section of that diagram is actually for us, it's quite small down at the bottom, right? Like once you get up above about 800, we're already kind of getting outside our flyable range. So it's easy sometimes to get confused if you're looking at the QT. to think that the day is actually the entire diagram, but the reality is what we're looking at is just that little section at the bottom, right?
Right, yeah, so keep in mind here that like, here's like this changes, but if we talk about standard height here, 925 millibars is 2,500 feet. So essentially 3,000 feet is right here. And so if we zoom in on this, the entire profile is completely stable for the most part. As we know, sometimes you can get micro pockets that can end up working, you know, if that air is being held to the ground and it continues heating and heating and heating, eventually that parcel of air will get hot enough that it will actually rise a little bit through the atmosphere. We know that it being completely stable doesn't mean that it's not flyable, but it really does tell you that the air is not going to be unstable and it's not going to continue to keep on rising, and it's going to be sort of like a better fly day. I'm going to go back to my iPad now. So, okay. So now, just to make sort of like the visual representation. So if we have that red line being like this is unstable. This is my go to no. And this over here is stable. And the idea here is that if we ended up having, let's just say this dry adiabatic lapse rate of this, right? If we were on a stable day, the parcel would only rise to here. On a go to no day, it would rise to here. But on an unstable day, it would continue to rise until possibly the top of the tropopause, okay? So that's basically why, very simply, we can look at lapse rates in just this very simple way. Now let's talk about what a wet adiabatic lapse rate is. So, if we want to evaporate water, okay? We want water to turn into vapor. And in order to do that, we have to put a considerable amount of energy into this system, okay? We know that this occurs with like boiling water. It's a really obvious thing, but truly if you leave a glass of water out on the table, it will end up evaporating anyways. It doesn't have to be boiling. But the more energy that you put into sort of that cup of water or whatnot, the more excited the water will be on the surface and more likely it will be to jump into the atmosphere. And so the more energy, the more vapor you have. But the point is that in order to make that jump, it takes a significant amount of energy to occur. Now, if we go the opposite way, and we go from vapor to water, okay, this ends up releasing energy, okay? And so basically the idea is that we have our little parcel. It's going up in the atmosphere, right? If we do this as z and this as temperature, so altitude on the y-axis and temperature on the x-axis, we're cooling until we reach something here called the LCL, or it could be the CCL too, okay? So basically at this level is where the parcel air will start condensating, okay? The idea is that as air cools, it sort of basically has like less available space for water. And so at a certain point, those water molecules will have to pop out of the air, it'll pop out of vapor, and it'll end up going into water form. So when that happens, you end up getting condensation, okay? And when we end up getting condensation, we end up getting this release of energy. And so we have sort of like condensation occurs, right? And we have this release of energy into our air parcel. So now if we are decreasing our temperature as we go up in height, and we start adding energy into the parcel, it basically means that once we condensate, we will cool at a lower rate as long as we are still condensating water. Okay, and so if we have like 9.8 degrees C per kilometer, right, and we're cooling, and we add in basically 3.8 degrees C per kilometer, okay, this ends up decreasing our lapse rate to 6 degrees C per kilometer. All right, it's a good number to use. It's just to understand it. It does change with the amount of condensation and moisture that's basically occurring. But this is sort of like, again, another critical concept, right? We are decreasing our temperature with altitude. If we end up adding heat into that with this 3.8 here, right, it will end up decreasing the rate at which we decrease our temperature. Does that make sense?
So far, so good.
So far, so good. Okay.
But Chris, basically, that happens above the cloud base, right?
So it would happen at the cloud base. And basically, we could think, so if we have this graph here where we have sort of like our, let's say our unstable profile here, and if we're following along this profile, right, along this section down here, if we end up condensating, right, we will end up cooling at a lower rate here. And as this distance increases, we basically have a larger gradient, and the energy of the system, like the movement of the air, is going to be faster, okay? And this is basically like the idea that would be cloud suck, okay? As you start condensating water, you decrease the lapse rate, which ends up making the air even more unstable, which is basically, yeah, which is and ends up being cloud suck.
Would another way of thinking about that be that, so in other words, that air mass now has to rise higher to achieve the same level of cooling? Is that totally erroneous?
Yes, that's true. Yeah. Yeah.
And is that LCL or CCL line, is that what we would consider to be the dew point where we see that condensation occur, or is that a different concept?
That would be when the air reaches the dew point, which is also not a simple idea as well. But yes, that is when the LCL or the CCL would be when the air reaches the dew point. But remember that the dew point changes with altitude by its own, I don't know what you call it, like the mixing, it's like the mixing ratio on the SKUT, which I can sort of walk through. I'm not like super clear on that.
Some
but
people just call it voodoo.
Yeah, voodoo magic. So just to go over this, so the LCL, let's see if I can do this. So if we have like a mountain here, okay, and we have air shoved into this mountain, and then it goes up, okay. The point at which it reaches condensation here is the lifting condensation level, okay. But alternatively, if we have a parcel of air on the ground that heats up in order to rise, it will have a greater temperature at this position 2 than position 1. Therefore, it will have to cool further in order to condensate. And that's why we have the cloud condensation level as well. And you'll see these on SKUTs. It's on Windy. You can see them But I just described those two because they are two different processes. Cool. What do we think about that stuff?
So far, so good.
So Chris, am I wrong that my understanding was that the cloud base is basically when the in the skew T line, skew T graph, basically the temperature line, and then there is a dew point line. When those two crosses, that will be the where the condensation is happening. Therefore, there will be the cloud base. Am I wrong?
That's both true and a little too simple. It does occur that way, but you can also get clouds through just simply through lifting the parcel. We can go to that real quick. See if we can go back. So maybe I can zoom in on this one.
Sorry that I'm a little sensitive about cloud for some reason.
Yeah, that's great, Sangwon. These are great questions. So, okay, so Sangwon is correct. If these two lines ends up touching each other, you will end up having clouds. Okay, that is basically like the air mass that is coming in will already have clouds in it. But some days these lines will not be touching each other, and we will also get clouds too. So I guess I don't have it anymore. Let me see if I have this still. Yeah, damn, I don't see it really accessible. Check one more place. Yeah, here we go. So not only do we have maybe this doesn't show it super well, but not only do we have sort of like a lapse rate by itself, but the dew point also changes with altitude, right? Because as the temperature is changing as we go up in height, it doesn't follow this line. Just like if we have a parcel of air on the ground, it doesn't follow this temperature profile. There is sort of like another line that we are looking at here to try and understand whether clouds would form. And so I believe on this graph, it is these numbers here, or at least they look like they're going in the right direction. But basically, if this line was closer over here, so let's say if this moved over here somewhere, all right, if we wanted to understand if that would end up creating clouds, we'd basically just follow this mixing ratio up to where it hits the environmental lapse rate. And
hey, Chris.
Yeah.
What are you pointing? I still see your laptop screens. Are you looking at a skew T chart?
Oh, sorry.
Here we go. Yeah.
All right. Sorry, my bad. Okay, so let's say if we just can I draw this actually? All right, I mean, this isn't super clear, but if I drew this line over here, okay, if I wanted to know where the clouds would occur, if I would end up lifting them through this adiabatic process, we would basically follow, I believe it is these lines here, like I was saying. I believe these are the mixing ratio lines. And we basically just take this and follow it up to the environmental lapse rate. And so if the parcel of air would rise to this altitude, you would essentially end up cooling the air enough so that you would end up getting clouds. Okay, and that's basically what determines the cloud condensation level. Is that so, Jali? Hopefully that answers, or I'm sorry, Sangwan. Hopefully that answers your question.
Yeah. Thank you.
Yeah, right. So there's sort of two different ways that we can end up getting clouds, basically. Okay, and so finally, I'll end up talking about what are sort of these two lines here. Where do we get them from? So if I go back to, so the example that I sort of thought of was for here in Santa Barbara. Okay, and so if we ended up having we have our water out in the ocean, which generally has cold air, all right? And then we have our land and our mountain here. Over the land, because the land heats more easily than the ocean, this air is generally hotter, okay? And basically, as our day ends up progressing, this air will come up and it will be replaced by this air. And so then our situation will end up looking more like this, where we have, oh God. Where we have cold air below hot air. And if we would do that on a skew T, okay, where we have temperature here and I mean, it's pressure over here, okay. So basically what it would end up looking like is that we have the cold air over the warm air. And so it'll end up, if we go from this air mass to this air mass, we are warming, okay? And then as we get into this air mass, we basically follow the rules of the atmosphere, and then we will end up cooling, okay? And so this is often what we see in Santa Barbara a lot, right? Because we have that ocean air that ends up coming in, especially in the summer. It can also happen overnight because the ground will cool off faster than the atmosphere. And that cooling of the ground will affect the atmosphere just above it. And you can end up getting that same situation where you have a small layer of cold air next to the ground. And sort of this air up here wasn't really necessarily affected by it. And so when we wake up in the morning, we often see this case where our lapse rate looks like this over here. Another thing that I was thinking of is that we could sort of have yeah, whatever that example. The other thing we like to talk about a lot is when cold fronts come through. Okay, and so when cold fronts come through, cold fronts generally can have a lot of force to essentially take whatever air was over here and just shove it up. And when that'll occur, we can end up just getting one clean air mass. Let's say this is the head of the front, okay? And so we can end up getting just a very clean air mass. And so with that, if we have a very clean air mass where we don't have sort of like, again, this cold air sitting below hot air, if we just have a clean air mass, then this can end up just following the rules of the atmosphere, where basically we're just talking about how much weight is above you, right? And this will end up just cooling at a constant rate, okay? And so that's why we generally think that when we have a cold front come through, that environmental lapse rate will end up looking something like this up here, right? Which hopefully will end up matching our, oh, that's a terrible line. Will hopefully end up matching our dry adiabatic lapse rate lines, right? And that's why we sort of get the most instability on those days.
So is that the case, Chris, then with like post-frontal where that cold front is moved through and there's clean air following in behind it? Or is this all part of that clean air parcel of the cold front?
Yeah, that's exactly what we're talking about. Yeah, if the front basically has enough energy to basically clean everything out, then yeah, we can get this very nice clean atmospheric profile that doesn't have a mixing of a bunch of different layers going on, and those end up being the best days for flying, and that's what we're talking about with post-frontal. And so that's pretty much what I was planning on covering for y'all today. That's an hour of me talking and rambling, so I think that's pretty good as well. And yeah, so I'll open up for just general questions, or if people want to add anything in, I'd be stoked to hear your ideas.
So just going back to the concept of parcels of air, thinking
Mhm.
about real world examples, are we talking about here in the mountains of Santa Barbara, are we talking about sort of air that's trapped along the slope in bushes and things like that, or down in a small pocket where it's heating up over the course of the morning hours and then it releases? Or are we talking about something that's more theoretical?
No, that's exactly what we're talking about. The parcel of air would be the air that starts off right next to the ground, and it starts heating because it is next to the ground through conduction. And as it starts sort of like getting hot enough and expanding enough and lifts off the ground, then it's sort of like, that's why we end up describing it as a parcel. And so it's exactly what you're talking about. It's any air that would be next to the ground, basically.
Cool.
I did have one more thing that I wanted to show, actually. I just wanted to remind people that yeah, so I mean, this is always fun to look at, okay? And so I just wanted to remind people this is essentially what we're trying to predict with computer models, and this is really what thermals look like, right? It is not just a clean column of air that is rising. It can twist and turn. It can have pieces that are intermittent. It can have pieces that can chunk off. And I don't know, I mean, moisture in the air is very cool. It's the only way that we can really see sort of like the dynamics that are going on. And I have one other example of ramen that looks very different, right? But you can sort of see this, that these pieces are sort of like, yes, it is a consistent column of air. Yes, it is all going in the same direction, but there's a lot of like pieces chunking off, and some pieces that are moving faster than another, and some that are moving a little bit slower than another, right? And we are sort of just trying to circle and stay in this piece to maximize the amount of lift that is occurring, but it's not always just like this constant thing that we sort of describe it as.
So would all that stuff over your bowl of ramen still be subject to the same rules of physics that we're looking at in the SKUT?
Absolutely, yes.
So if we just got a giant bowl of ramen and kind of placed it somewhere down near Parma, would be awesome, right?
It would be, if I mean, sadly, I mean, it's why global warming is good for paragliding. I mean, it's bad in the way that it'll change the dynamics that happen at our site, but the more energy you put into the surface, the more you will have to release that energy from the surface, and the more thermals and the faster thermals you will end up having.
Silver linings.
Silver lining, yeah.
Thanks, Professor Heckman. That was awesome.
Yeah, I hope you all learned something.
Thanks, dude.
Yeah, man.
Yeah, thanks a lot.